Hello and good morning. I'm going to go ahead and get to the right slide here for the beginning. And this is Mr. Hill. We're going to talk about metallic compounds. We did speak on or go over yesterday with the metallic bonds. And that's very important to understand that first. And we saw how there is a similarity between ionic bonds and metallic bonds. So let's go ahead. Now, metallic bonding, just as a review, has a lattice, just like ionic bonds do. So we see this lattice fence is what it's called. So you can have gaps in between where the intersections are of the pieces of wood, and that could represent the intersections, the stationary atoms or ions, and the empty spaces is where in the ionic bonding, where nothing is actually able to move around in because the bonds are so tightly packed with the atoms or the ions that's part of the bonds that nothing can move, not even electrons. But in a metal lattice, this represents again similar lattice structure, but there are gaps in between the atoms that allow electrons to freely roam. And that has a lot to do with the fact that metals have way more shells than nonmetals, if you will. And so metals and nonmetal bonding is what form ionic bonds. Metallic bondings or form bonds between metals, and that's called a lattice. And so the metals occupy the fixed positions and electrons float between them. Now I know on the slide it has it where no, it says the same thing, and it's called the sea of electrons, as far as the electrons flowing around the fixed electrons, fixed atoms, if you will. So I don't want to confuse nobody. The fixed atoms, ions of the metals have it where they're stationary, but the electrons basically flow around, swim around in that type of order. Now, metals do form what's called alloys. Alloys are used in industry or industries in very many places, and we'll see that next. I don't want to jump ahead of the slides. So we have metals that really they bond, but they don't really bond as we've seen thus far. What they do is they are more so a bonded metal solution that you would think it would make it be a mixture, but actually it's not, because there are bonds that form between the uh, the two metals, but because the electrons are able to freely move around in the lattice structure, it makes it where it's not seen in the classification of a ionic bond, where again things are very tightly packed between the ions or the atoms of those elements that make up that compound, and therefore there is no flow or movement of electrons. But metal lattices have a lattice structure, which means that the structure repeats itself. It is redundant. So it has a redundancy of a structure, but the electrons are able to move freely. And the ions of the metals mixed in this alloy stay in one position where they do not move. So that's the difference between ionic bonds and metallic bonds. Similar in lattice structure, but the electrons can freely move in a metallic one. So here's examples of this type of thing is steel, brass, bronze, and pewter. Alloys are based on strength, ductility. Ductility means how it can be drawn into a thin cord or wire. Copper, for example, you can press copper through what's called a injection mold, which forms the metal to be in whatever shape you want it to form into, and you can make it thinned out into a line or into a coil of wire, if you will, and that wire will have the density structure needed. It will not break down. It will still keep its density and function. The electrical conductivity, because of that, you have a sea of electrons around the ions of metals. You can also apply a force, and that force is you described as current, which entails there's a voltage being applied so it can conduct electricity. It can actually conduct the flow of electrons, if you will. And luster is how bright it is. You shine metals up, make them very bright. They're very strong materials, of course, and atoms have a strong attraction forces between them. So that's what makes metals very interesting, is that the forces between the metal ions are very strong, which is electromagnetism, by the way, and that they are very attracted towards one another. But their structures allow the electrons to move around freely around the fixed positions of the metallic ions or metallic atoms. And therefore, it takes a lot of energy. So that means we have a high temperature for melting or boiling points, and it also have a high. Uh, we also have some very interesting temperatures for how it freezes. Metals freezing work a little bit different. That's another story for another time. But high melting and boiling points, which means that it's going to take a high amount of energy, which is usually in many cases is converted over as a catalyst by applying heat or electricity or some type of high energy to it to help break those bonds, to cause that chemical reaction, bonds breaking, bonds forming, if you will. And that also means because they have a high melting and boiling point, they're very poor conductors in water or a aqueous or an aqueous solution, if you will. So here are some alloys. You have copper and tin mixed bronze. Brass is copper plus zinc. Pewter is tin and other metals such as antimony, uh, silver, lead, or bismuth. Steel is alloy of iron plus something else. Usually it's iron plus carbon. It's been that way for about over 100 years, but nowadays it could be iron plus something else. And we see all these metals, but especially steel, being used in a lot of household materials. Anything around the house, such as your microwave, stove, dishwasher, your refrigerator, even uh, the washer and dryer for clothes, same thing. Most of your vehicles, even your crossover vehicles, SUVs, are using some type of steel or a steel alloy of some sort. It might be steel, it might be steel carbon, like steel. Well, steel's actually is a alloy, is basically carbon and iron, but it might be iron plus some other element, if you will. And also, some cars even use what's called aluminum alloys. So you have an alloy of you have aluminum, iron and carbon put together, or you have an alloy of aluminum and copper, for example, which means you can make very high, durable, very strong structures, but very lightweight. So again, I pretty much kind of went into this already. Now the magnets and loudspeakers, and this is some more examples of alloys. The magnets and loudspeakers are usually the result of an electric magnet in some cases, or what is called neodyme magnets. Now, neodyme magnets is was a compound made by the research company, which is now a part of GM, but it was a research company for GM back in, I believe, the late 80s or early 90s, and manufactured neodyme magnets, which are very strong. I believe they're at least three times the strength of natural magnets that occur in the universe, or the clay magnets. And then they also can conduct electricity and become electric magnet when applied electricity to them. Also, dental fillings, the old metal ones, those are actually alloy. And also, if you use hand tools at home, things like skills, Ryobi, Craftsman's, or Black and Decker, as far as drills, electric tools, or power tools, like you want to call them, the motors inside those power drills, for example, when they rotate around, they usually have a brush, and that brush is a part of how it actually can determine the direction of the motor spinning. If you make it frictionless, you usually have a compound of carbon in conjunction with some other metal, and what it does, it actually keeps the surface polished of the rotating part of the motor, of electric motor, and that keeps it from rusting out, breaking down too quick, and actually reduces the friction. The smoother something can move by, the less friction you have. So door locks and bolts, instruments, and we do have things over here like automobile parts, military equipment, guns, nuclear weapons, and much more. Alloys are used all around us in everyday life. Your iPad, for example, or your computer has alloys in it. All right, now the physical properties of metals is lustrous. It has the ability to shine, high density. Atoms are packed tight. This, again, similarity to ionic compounds, ionic bonds, tightly packed atoms. The difference between ionic compounds and ionic bonds versus metallic compounds and metallic bonds is the fact that in metallic bonds, the electrons are able to freely move. Keep in mind, sea of electrons. You have the ions that are metallic or the metallic atoms stationary, meaning they are not moving. They are positioned, they are there. It is what it is. And they're attracted towards one another and they're held together. But their electrons outside of them on the outer shells or the valence shell of each of the metals that part of this alloy are freely moving around. You don't have that in ionic compounds because ionic compounds make it where you have to have the salt itself that it forms, which is part metal, part non-metal, be separated or disassociated in water for it to conduct electricity. Metals make it where it can stay as it is at room temperature as a solid and conduct electricity because it has the sea of electrons. I know I sound like a broken record, but I just want to stress that very clear to everyone. And it's not to be senile, it's to be very clear. This is very important of the difference. They are good conductors because of this, and also of heat and electricity. A lot of times, heat is the result of a loss of energy. And I said loss of electricity, but that's not true. It's the loss of heat is a loss of energy, is what it's referred to as. And you can use that to your advantage. When you make electric heaters or electric blankets, we are purposely using the thing called entropy to create the loss of heat from a system or the loss of energy to heat someone's body or environment, if you will. Also, it's ductile and it can be drawn into wires and it's moldable. I mean, you can hammer it into different shapes. You can do that with metal itself. You can actually push the you can push the metallic ions or metallic atoms, if you will, into a different part of the metal, or you can actually stretch it out and push it around within the same metal. You can beat it and stretch it out. You can actually take metal and press it and make rolls of metal or sheets of metal or what they call sheet metal, or even have the metal stretch where you can make a sheet of metal with a certain thickness and you can press down on it and make a pot, if you will. Also, ionic compounds versus metallic compounds. They are brittle and break easy as far as ionic compounds. Why? Well, physical properties. They are arranged in a very compact order pattern, similar to the way apples and oranges are stacked at the grocery store, as you can see in the pictures here. Pure metals from the simplest kinds of crystals, meaning that these metals are actually not made into an alloy. They're actually mixed and they come together with a non-metal. That's the reason, which hence makes it where it's brittle. Also, the chemical properties of metal is that most of them are chemically unstable and will react to oxygen and air, which forms oxides, which means that, in other words, it forms some kind of rust. And we do see in this picture right here that there is a rust from an iron 3 oxide. And the reason I say iron 3 because it's the charge of a positive 3 that's being used because some metals have different charges under different conditions, if you will. But iron oxide is rust, and that's the same rust that's used to magnetize your debit cards, credit cards, even when you use fobs to get in and out of buildings, if you will, because the information that is used on a debit card, credit card, or a fob, FOB, or I believe it's PFOB, to actually get into somewhere, it is it is programmed on a magnetized strip, if you will. And also, you can see over here, this is, I believe, uh, potassium uh, reacting potassium oxide or potassium chloride in some kind of way, forming that alternative table salt, if you will. And these come together and they form oxides. Now, keep in mind, oxides does not mean it has to be oxygen. An oxide can be where any type of metal forms a certain type of rust or rust-like compound, when it reacts to some other gas or other gases in the air in itself. But oxides is used as a or oxidation, if you will, is used as an old school term that stuck for a number of years. But basically, when metal begin to rust, it forms oxide. Also, alkaline metals react the quickest, followed by the alkaline earth metals. And transition metals take much longer to oxidize, like iron, copper, zinc, and nickel. Others like palladium, platinum, and gold do not react with the atmosphere at all. Now, aluminum does. I want to mention aluminum, and it's actually the next thing, and I'm going to mention this for a certain reason. 'Cause aluminum is very special in the sense that it was not the easiest thing to separate in the atmosphere, and it acts a lot different than iron. So we have metals that form a barrier of a layer of oxide on the surface, which cannot be penetrated by the oxygen molecules, and you get like this white ash that forms on the surface, and that's what you get with aluminum or aluminum oxide. Next time you see a house that may be older, if you see the aluminum siding starting to lose the paint on it, you may look at how the aluminum starts to look like this kind of whitish gray look. That whitish gray substance is aluminum oxide, and it does form a barrier where nothing else can get into it. So it forms what's called an erosion coat, and that happens with some metals and compounds that there's a coat of erosion on top of it, which means that the metal is interacting with the things in the air or in the atmosphere around it, and over time, that target metal will turn into that to that erosion compound there, if you will. And so, aluminum, some steels, and titanium does this quite often. Now, alloys are very few that there are very few that you alloys all around us basically, and there are very few pure metals that actually are around. So in other words, you're dealing with some mixture of something. So never assume that any metal that you deal with, unless you got it from a factory as raw materials that's about to be processed, or you went and dig it up the ground yourself, and something's going to be 100% of anything. So brass, sterling silver, and even stainless steel are all falls into things like alloys, even gold that you wear. That's why we have things called carat, 24 carats, and let you know that there's that much. There's 24 carats of gold in the thing you're wearing, and it's mixed with other metals because gold is a very soft metal. For example, it's not a metal that can actually harden up, and so therefore it's mixed with other metals so it can become a solid. Sterling silver, same thing. 90% of it is actually silver. 8% is copper. Stainless steel, 81% is iron, and chromium is 18%, nickel is 1%, and there's trace amounts of carbon. So you can actually, again, hear and see things in the atmosphere around you that is a mixture more than you may realize, myself included. So allies are important because they actually give us the ability to make products, devices to be durable and solid. So all the wonderful applications we enjoy with technology and electronics, a lot of that came from the advancements of alloys, if you will. All right. So for the virtual assignment, go ahead and you want to do the metallic compound assignment, get 10 tries. Any questions you have, please feel free to contact me through Schoology or even at jhill at lakelandlakers.net. Thank you.